You're probably familiar with that feeling of information overload, right? You've got stacks of articles, endless reports, maybe research papers, and you're thinking, how do I quickly cut through all this noise? How do I get to what really matters? And it turns out artificial intelligence, especially the kind that works in teams, well, it grapples with pretty much the same challenge.
It really does.
So here on the deep dive, we do the heavy lifting for you. We take that stack of sources, pull out the key nuggets of knowledge and insight, and basically give you a shortcut to being truly well-informed.
That's the goal.
Today, we're taking a deep dive into two, I think, really fascinating and deeply interconnected areas of AI. We're looking at multi-agent systems, often called MAS, and also the sort of cutting-edge field of context engineering for large language model.
Yeah, and for this deep dive, our sources are quite varied. We've got some foundational texts on multi-agent systems from Michael Wooldridge, for example. But we're also looking at recent research articles from places like Smitho, SingleStore, and preprints from ArcSift. These really explore the latest advancements in AI communication, the inherent challenges, and also the really nuanced ways that LLMs process information.
Okay, so our mission today is to unpack what these, let's face it, complex concepts actually mean. We want to explore the big hurdles they face, maybe highlight some surprising applications, and most importantly, show you how they weave together, how they intertwine to shape the future of AI and how we interact with it. So let's break this down.
Let's do it.
Okay, let's start right at the fundamentals. When we talk about AI in this way, what exactly is an agent, and what makes a system multi-agent?
Right, so think of an agent as a smart, independent piece of software. It's a kind of computational entity. It can keep track of its own state, perform actions, decide what to do, and crucially, communicate with others.
Okay.
And what's really interesting, I think, is how they differ from, say, traditional software objects that programmers are used to. Objects, they control their internal state, sure. But agents, they go a step further. They actually decide for themselves whether to perform an action if you ask them to. So they exhibit this stronger sense of autonomy, but it's autonomy over their behavior.
Ah, okay. So it's not just data, it's action.
Exactly. And they're also inherently multi-threaded. They can juggle multiple things at once, sort of like us. And they're capable of being flexible, proactive, acting on their own initiative and social, interacting with others.
So definitely not just lines of code following a rigid script then. Can you maybe paint a real-world picture for us? Give us an example.
Absolutely. Think about maybe a space probe. It loses contact with Earth, deep space mission, but it figures out something's wrong, diagnoses a fault autonomously, and maybe reorients itself to try and reestablish contact, all without human input.
Wow, okay.
Or something maybe a bit closer to home. Imagine your personal digital assistant, your PDA. It doesn't just fetch information. It actually negotiates with various websites on your behalf to book a whole holiday, finding flights, hotels, maybe a hire car, coordinating all those pieces.
Right, integrating different services.
Precisely.
Yeah.
These aren't single programs doing one thing. They're systems where multiple autonomous entities are interacting to achieve some larger goal.
And that's where the multi comes in, I suppose. But what's the really big difference compared to, say, a traditional distributed system? Because those also involve multiple computers working together.
Yeah, that's a great question. And this is where it gets, I think, really insightful. In a classic distributed system, all the computing parts, they typically share a common goal, right? And how they coordinate is usually hardwired when the system is designed. It's fixed.
Okay.
In multi-agent systems, however, the assumption is often different. Agents are frequently assumed to be, self-interested. They're primarily concerned with their own welfare, their own objectives, even if they are working towards some common broader goal.
Interesting. So potentially conflicting motives.
Potentially, yes.
Yeah.
Or at least different priorities.
Yeah.
And this means they need dynamic mechanisms.
Yeah.
They need ways to synchronize and coordinate what they're doing at runtime. They have to adapt on the fly rather than having everything prescribed beforehand.
Right.
The key takeaway really is moving from AI that just follows instructions passively to AI that actually decides and negotiates. And that fundamentally changes how we think about building and trusting these systems.
Okay, so if these agents are, as you say, self-interested, how on earth do they manage to cooperate? How do they actually get things done together? Communication must be just absolutely vital.
It is. It's paramount, really.
Yeah.
And AI-enhanced communication is key here. It allows agents to make intelligent decisions about when to share information and how to share it. It moves way beyond static, predefined rules.
So they learn how to communicate effectively.
Exactly. They can learn optimal strategies, often through experience, through trial and error. This leads to interactions that are much more nuanced, more context-aware. Advanced techniques like deep reinforcement learning, where agents learn kind of like we do, trying things, seeing what works, helps them develop really sophisticated protocols. They figure out how to share the critical stuff while minimizing, just noise, unnecessary chatter.
Okay, what does that communication actually look like? Is it like humans talking, or is it just data packets?
It's sort of like humans talking, but much more formalized. They use something called speech acts.
Speech?
Yeah, they're like predefined labels for the intention behind a message. So instead of just sending raw data, an agent might send a request, which basically means, hey, I need you to do this thing for me.
Mm-hmm.
Or it might send an inform saying, here's something I believe is true and probably relevant to you.
Got it. So it adds context to the message itself.
Precisely.
Yeah.
And there are special languages like KQML that stands for Knowledge, Query, and Manipulation Language. These define a common structure, a format for these messages. It's almost like a universal grammar, so different agents, maybe built by different teams, can actually understand each other's intentions.
Okay.
And this allows for both proactive sharing. An agent shares something because it thinks another agent will find it useful, and reactive sharing. Responding to a direct request.
It sounds incredibly powerful, incredibly promising. But, with interactions this complex and agents being autonomous, I imagine there must be some pretty significant hurdles. What do you see as the biggest challenges in actually building and deploying these MAS?
That's an excellent point. And yes, there are definitely several quite intricate challenges that demand a lot of attention. First off, interoperability. This is a really critical hurdle. You have agents built on different platforms, maybe by different teams, and they often end up speaking different languages,
Right.
metaphorically speaking.
Right.
Lack of standardized protocols really hinders collaboration. So solving that is absolutely essential if we want truly integrated systems.
Okay, that makes sense. What else?
Second, just managing the complex interactions. As these systems grow, you get this web of relationships, dependencies between agents, and it can grow exponentially complex. Coordinating actions, figuring out how to resolve conflicts when agents have different ideas, maintaining coherence across the whole system. It requires a really deep understanding of how these autonomous entities can actually work together effectively while still pursuing their own goals.
Designing those coordination mechanisms must be, well, a real head-scratcher sometimes.
I can imagine.
Yeah.
Then there's scalability and resource management. Making sure the system performs well as it gets bigger, as you add more agents, that's a constant challenge. You need techniques like dynamic load balancing, decentralized decision-making, so agents can sort of adjust their own resource use without some central controller constantly managing everything.
Right, letting them self-organize to some extent.
Exactly. And platforms like Smithos are being explicitly designed with architectures that aim to provide automatic real-time scaling to handle those fluctuating demands. That's a big step forward.
Okay. Technical challenges. What about other aspects?
Absolutely. Then we get into ethical considerations. This is huge.
Yeah.
Designing AI agents that can navigate complex moral landscapes, that's critical. It involves trying to implement moral reasoning algorithms, setting clear boundaries on what agents can and cannot do, prioritizing transparency so we understand why they make certain choices.
But that sounds incredibly difficult, defining universal morals.
It is. It's a massive challenge. Defining universally accepted moral principles is, frankly, an ongoing philosophical debate, even for humans. It gets complicated by cultural differences. And there's always the risk, with these complex systems, of unintended consequences popping up from unexpected interactions.
Yeah, the law of unintended consequences looms large.
It does. And finally, related to that is security and privacy. Protecting sensitive data is just paramount. You need things like end-to-end encryption for data, both when it's moving and when it's stored. Strong authentication, making sure agents really are who they say they are. And also privacy-preserving techniques, things like differential privacy.
Differential privacy, how does that work briefly?
Well, the idea is you cleverly introduce a tiny bit of controlled randomness or noise into the data before sharing or analysis. It's done in such a way that it makes it practically impossible to pinpoint any single individual's exact information from the data set. But crucially, you can still see the overall patterns and trends when you look at the data in aggregate. So it protects individuals while allowing for useful analysis.
Clever. Okay. So it seems like beyond all the technical nuts and bolts, there's this really profound need for these systems to be, well, aligned with human goals and values, especially given their autonomy.
Precisely. Ultimately, I think the biggest challenges really lie in, one, maximizing each agent's unique capabilities, letting them do what they're good at. Two, aligning all those individual tasks with the overall goal of the system. And three, really understanding the overarching context for those tasks. Why are they doing what they're doing? And this isn't just a technical programming problem, right? It's a fundamental design philosophy. It requires deep thought about purpose and values.
That idea you just mentioned, understanding the overarching context, it feels like a perfect bridge, actually. It brings us right to our next big topic. Context engineering, especially when we talk about large language models, LLMs. How does this context engineering thing go beyond what most of us might think of as just, prompt engineering?
Okay, yeah, let's unpack that distinction because it's important. Prompt engineering, which many people are trying now, involves carefully crafting the input text, the prompt, to get a specific desired response from an LLM.
Right, telling it what you want.
Exactly.
Yeah.
Context engineering, though, is much broader. It's a more comprehensive discipline. It's really about constructing the entire information environment that the LLM operates within, making sure it has everything it needs to handle whatever comes its way effectively.
The entire environment. What does that include?
Well, the LLM's prompt, in this view, isn't just that single text string you typed. It's the whole context window. That's this kind of dynamic informational bubble that includes things like the initial system instructions, you are a helpful assistant, etc. It includes the history of the current conversation, any outputs from tools the LLM might have used, like a calculator or a search engine, and importantly, any relevant text retrieved from external knowledge sources. It's about curating all of that.
Okay, so it's much more than just the user's question. It's about curating everything the model sees, everything it's exposed to. Now, where does retrieval augmented generation, RAG, fit into this? That's a term popping up everywhere lately.
RAG is a perfect example of a key component within this broader context engineering approach.
Okay.
RAG basically combines a search step with the LLM. Before generating a response, it fetches relevant, hopefully authoritative passages from some external knowledge store, like a database of documents. And then it injects those passages right into the context window, into the prompt.
So it gives the LLM facts to work with.
Exactly. It grounds the LLM's response in factual data, which sharply reduces those notorious hallucinations or incorrect statements.
Makes sense.
So context engineering is the bigger craft. It's about curating all these elements, the instructions, the history, the RAG output, maybe other things, and arranging them optimally within that context window, which, by the way, is often quite limited in size.
Right, that limited window size is a key constraint, isn't it?
It is. A major constraint that context engineering tries to manage effectively.
And how does something like semantic search play into this bigger picture of context?
Oh, semantic search is absolutely fundamental here. It's often the engine behind effective RAG, for instance. Unlike traditional keyword matching, semantic search focuses on understanding the intent, the meaning, the context behind a user's query.
Not just the words they used.
Precisely. It uses natural language processing, machine learning, to grasp what the user's really asking for, leading to much more accurate and relevant results. And for generative AI, this is crucial because it's not just about finding information anymore. It's about generating content, maybe a story, an explanation, some code that truly aligns with the user's underlying intent.
Okay, this is fascinating. So we've explored agents as these smart, independent problem solvers, and we've looked at context engineering as this craft of building the perfect informational environment for LLMs. Now, the really exciting part, and I think where this deep dive truly connects the dots, is how these two powerful ideas aren't just running in parallel. They seem to be actually converging. How exactly do multi-agent systems and context engineering come together?
Well, this is where it gets really interesting and quite cutting edge. The latest research, and specifically there's a paper, a survey of context engineering for large language models, it explicitly identifies multi-agent systems. It calls them out as one of these sophisticated implementations, one of the architectural approaches for integrating all these different context engineering components together.
Wow, okay. So you're saying an MAS, a multi-agent system, can actually be the dynamic system that provides the context to an LLM. That sounds incredibly powerful. What does that mean architecturally if someone's trying to build this?
Precisely.
Yeah.
Yeah, architecturally, imagine this. You have a multi-agent system where different agents specialize. Maybe one agent is an expert at context retrieval. It knows how to find the best documents using semantic search.
Okay.
Another agent is great at processing that information, maybe summarizing it or extracting key entities. A third agent could be responsible for managing that limited context window, deciding what information is most important to keep in view right now.
Like a conductor for the context.
Sort of, yeah. And they all collaborate. They work together to feed the central LLM the perfect, curated, just-in-time information it needs for whatever complex task it's trying to accomplish.
That really mirrors how human teams work, doesn't it? Leveraging specialized skills, breaking down big problems.
Yeah. Exactly. It moves beyond the idea of a single monolithic LLM trying to do absolutely everything, which often struggles with complexity or conflicting demands. Instead, you have this distributed system of collaborating AI entities. The core insight here isn't just about making AI smarter in isolation, it's about enabling a whole new frontier of AI team play. You can tackle problems that might overwhelm a single AI model by having these specialized agents collaborate, much like, human experts solve complex problems together.
That feels like a really natural, maybe even inevitable evolution for both fields. If we zoom out, what are the broader implications of this convergence, connecting it back to the bigger picture?
Well, if we connect this back, think about those ethical considerations we discussed earlier for MAS. They become even more critical, arguably, when you combine autonomous agents with the power of LLMs generating content and making decisions based on engineered context. Ensuring that these complex, multi-agent, context-aware AI systems are designed with really clear ethical frameworks, with transparent decision-making processes. That's not just a technical hurdle. It's becoming a foundational challenge for the entire AI industry. It really requires not just engineers, but philosophers, ethicists, social scientists working together.
A multidisciplinary challenge.
Absolutely. And it also highlights that shared emphasis in both fields on continuous learning and adaptation. You have agents learning better strategies for cooperation and communication, and you have LLMs constantly adapting their outputs based on ever more sophisticated, dynamically engineered context.
Okay, looking ahead then, what's really on the cutting edge for these intertwined fields? What are the big, maybe unanswered questions that researchers are wrestling with right now?
Well, that survey on context engineering I mentioned, it identifies a really critical research gap. It points out that while current LLMs, especially when augmented with advanced context engineering techniques like RAG and semantic search, show really remarkable skill in understanding complex contexts.
Right, they can process a lot of info.
They can, but they still have quite pronounced limitations in generating equally sophisticated, coherent, long-form outputs based on that understanding. There's this kind of asymmetry between their comprehension abilities and their generation abilities, especially for complex, lengthy tasks. Addressing that asymmetry is seen as a major priority for future research.
Interesting. So understanding is ahead of generation in a sense. What about for multi-agent systems themselves? Where are they being pushed? What are the frontiers there?
Oh, MAS are being pushed into increasingly realistic, often very challenging domains. Think about something like the RoboCup initiative. That's a famous example.
The robot soccer competition.
Exactly, robot soccer. But it's more than just a game. It aims to develop teams of autonomous robots that can cooperate dynamically. And there are related challenges, like search and rescue robots, designed for scenarios based on real-world disasters, the Kobe earthquake or the World Trade Center collapse. These robots need to coordinate their actions with potentially limited communication in unpredictable, high-stakes environments.
So these aren't just theoretical exercises in a lab. They're really pushing the boundaries of what autonomous cooperating AI can actually achieve out in the world.
Definitely. They're tackling real-world complexity. And that journey, as we touched on, towards truly ethical AI systems, both for individual agents and these complex multi-agent systems, it's incredibly complex. But figuring that out is, I think, one of the most important technological and philosophical challenges of our time.
So it really seems like whether we're talking about a team of AI agents coordinating a rescue effort or a sophisticated system carefully feeding an LLM the perfect context to generate a complex report, multi-agent systems and context engineering are really like two sides of the same coin. They're driving this next generation of intelligent, cooperative AI.
Deeply intertwined.
And as we continue to develop these increasingly advanced AI capabilities that promise to enhance human decision-making and problem-solving in some truly transformative ways, maybe here's something to mull over. What new forms of collaboration might emerge from these deeply intertwined fields? Not just collaboration between AI agents, but maybe new ways for humans and AI to collaborate as these systems continue to evolve together.
That's a great question to end on. Thank you for joining us for this deep dive. We really hope it sparks some new ideas for you and gave you some exciting insights to think about.